How do you visualize a quantum state for superposition? Imagine trying to picture a tiny particle that can be in two places at once or spin in multiple directions at the same time. Sounds strange, right? That's the magic of superposition in quantum mechanics. To understand it better, scientists use special tools to turn these abstract ideas into images we can grasp. One of the most common ways is with something called the Bloch sphere. Think of it as a globe where the North Pole represents the state 0 and the South Pole the state 1. Any point on the surface of this sphere shows a mix of these states. The position on the sphere tells us how likely the particle is to be in either state and how the phases of these states relate. It's like a map that shows all the possible superpositions a single quantum bit, or qubit, can have. But what if we have more than one qubit? That's where more complex visualizations come in. For multiple qubits, scientists use Q-spheres, which are like bigger globes with colors and sizes to show probabilities and phases. These colors can change to show how the quantum states evolve or interfere with each other. It's a way to see how multiple particles can be entangled or linked together in superposition. Another way to picture superposition is with probability clouds. Imagine a foggy landscape where the density of the fog shows where the particle might be found. The thicker the fog, the higher the chance of finding the particle there. Over time, this fog shifts and changes shape, showing how the quantum state evolves. These visualizations help us see the dynamic nature of superposition, even though the actual wave function is a complex mathematical object. Experiments like the double-slit experiment make superposition visible by showing interference patterns. When particles pass through two slits, they create a pattern that looks like waves overlapping. This pattern is proof that particles are in a superposition of paths. Advanced techniques, like scanning tunneling microscopy, can even visualize wave function directly in materials, revealing phase angles and complex quantum patterns. In the world of quantum computing, visualizing superposition helps us understand how qubits work together to process many possibilities at once. It's like a supercharged version of parallel processing, where the visual tools help researchers track how quantum information flows through circuits. So, to sum it up, visualizing a quantum state in superposition involves using models like the Bloch sphere, probability clouds, color-coded maps, and experimental images. These tools turn the abstract idea of multiple states existing at once into images we can understand, making the strange world of quantum mechanics a little more familiar and a lot more fascinating.